Micro-EDM and Micro-WEDM. Micro-EDM is a thermoelectric machining process in which there is no interaction between tool and workpiece. There is no machining force and mechanical stress to cause deformation of either workpiece or tool electrode. In Micro-EDM, material is eroded from the workpiece by a series of recurring sparks produced between the tool and workpiece submerged in a dielectric. It can machine any electrically conductive material regardless of its hardness and strength. Due to lower voltage and current used for few micro or nanoseconds, the material removed for each pulse duration is in the range of microgram, g. Advantages of micro-EDM systems are low tooling cost, high aspect ratio, improved precision and considerable design freedom. Principle of material removal mechanism in micro-EDM. Parameters such as assigned and controlled inter-electrode gap, voltage, energy per pulse, and frequency of spark discharge. The high geometrical accuracy and good surface quality, roughness of about 0.1 m, is achieved at high frequencies greater than 200 Hz and small discharge energies for each spark discharge in the range of voltage of 40 to 100 V. The discharge energy is supplied by a pulse generator and a servo system maintains the constant spark gap by moving the tool electrode at a suitable rate. Fresh dielectric is supplied into the spark gap by a dielectric circulation unit. The dielectric circulation unit consists of a pump, filter, and tank, maintains the proper flushing of debris materials from the machining zone. 3 important phases of the sparking. I. Preparation phase for ignition, 2. Discharge phase, and 3. Interval phase between discharges. When the suitable gap voltage is applied, an electric field with highest strength is produced between the tool electrode and workpiece. And the insulating properties of the dielectric fluid eventually breaks down due to the presence of this electrical field, ionizing. When the resistivity of the dielectric fluid is lowest, a single spark flows through the ionized flux tube and strikes the workpiece. At this stage, the voltage drops and the high current is passed. The spark produced between the tool electrode and workpiece melts and vaporizes the workpiece material in contact and creates a single crater. The dielectric fluid, which surrounds the spark, is also vaporizes along with the gases such as hydrogen, carbon, and other oxides. The thermal energy of spark and contaminates produced from workpiece temporarily disrupts the ionization of the dielectric fluid and thus, the resistivity increases rapidly. Initiation of electric discharge. Ionization and electron avalanche. Melting and evaporation. Repetition of cycle. Crater formation. Erosion by thermally generated pressure wave. Due to the increase of resistivity of the dielectric fluid, the stable spark no longer sustains and as a result the voltage rises and the current drops. At this stage, the current is switched off, using pulse interval. During the pulse off time, no spark is generated and heat source is eliminated. The covering of vapor around the spark collapses, creating a vacuum or void, and circulates fresh dielectric fluid to flush away debris material from the crater and cool the machining zone. Petroleum-based hydrocarbon, mineral oils, and ionized water are the 3 most commonly used dielectric fluids in micro-EDM. Different materials and its properties. Wire coil. Wire. Fed via wire guide coils. Control units. Collection coil. Dielectric supply deionized water. The spark gap. Diameter of the wire. Illustration of wire EDM. WEDM uses a single string of thin metal wire to cut thick metals for precise incisions. Deionized water as dielectric fluid. Automatic wire feed ensures the wire is never worn and cutting is consistent, resulting in repeatable accuracy. Advantages and disadvantages. Advantages. Can process all conductive materials. High finish on the cut surface. Small cut gap means that you get low removal volume. Handles tight internal radii. Very high utilization, high degree of automation. Touchless processing without cutting forces. Handles processing hard and brittle materials. Stable process. Can process heat-resistant materials. Quiet manufacturing method. Parallel cuts. Requires blasting often only as a final operation. Disadvantages. Micro cracks can occur in the cut surface. Larger details cannot be machined as thick work pieces slow the cutting process. Non-metallic coating, laminating is difficult to spark. Slow method. Risk of corrosion due to electrolyte. The cut will be extra sensitive to corrosion. Advantages of EDM. Any material that is electrically conductive can be cut using the EDM process. Hardened work pieces can be machined, eliminating the deformation caused by heat treatment. X, Y, and Z axis movements allow for the programming of complex profiles using simple electrodes. Complex die sections and molds can be produced accurately, faster, and at lower costs. The EDM process is burr-free. Thin fragile sections such as webs or fins can be easily machined without deforming the part. Disadvantages of EDM. The slow rate of material removal. Potential fire hazard associated with use of combustible oil-based dielectrics. The additional time and cost used for creating electrodes shapes. Reproducing sharp corners on the workpiece is difficult due to electrode wear. Specific power consumption is very high. Overcut is formed. Excessive tool wear occurs during machining. Electrically non-conductive materials can be machined only with specific setup of the process. Applications. Die making. Dies are tools used to cut or shape materials into a solid product. Mold making. Micro-nano systems manufacturing. Production of the micro-milling tools. Complex micro-drilling tools. Micro-molds for MEMS systems. Machining of microfluidic channels. Injection molds, and stamping dies. Micro-EBM. It uses a high-velocity stream of electrons focused on the workpiece surface to remove material by melting and vaporization. Mechanisms of material removal is thermal processes considering but electrical energy is used to generate high-energy electrons in EBM. Thus these processes are often classified as electrothermal processes. Electron beam is generated in an electron beam gun. Electron beam gun provides high-velocity electrons over a very small spot size. Electron beam machining is required to be carried out in vacuum. Otherwise the electrons would interact with the air molecules, thus they would lose their energy and cutting ability. The high-energy focused electron beam is made to impinge on the workpiece with a spot size of 10^100 μm. The kinetic energy of the high-velocity electrons is converted to heat energy as the electrons strike the work material. Due to high power density, instant melting and vaporization starts and melt vaporization front gradually progresses. Mechanism of material removal in electron beam machining. Localized heating by focused electron beam. Gradual formation of hole. Penetration till the auxiliary support. Removal due to high vapor pressure. Finally, the molten material, if any at the top of the front, is expelled from the cutting zone by the high vapor pressure at the lower part. The gun in EBM is used in pulsed mode. Holes can be drilled in thin sheets using a single pulse. For thicker plates, multiple pulses would be required. To minimize the thermal diffusion problem, it is recommended to pulse the beam or scan it rapidly across the surface to be machined. Arrangement of electron beam machining machine. The process parameters. The parameters are: removal rate, surface quality, accuracy, EBM pulse, time, power density, emission current, working material. Advantages. EBM provides very high drilling rates when small holes with large aspect ratio are to be drilled. Moreover, it can machine almost any material irrespective of their mechanical properties. As it applies no mechanical cutting force, work holding and fixturing cost is very less. Fragile and brittle materials can also be processed. The heat affected zone in EBM is rather less due to shorter pulses. EBM can provide holes of any shape by combining beam deflection using electromagnetic coils and the CNC table with high accuracy. Limitations. Need of vacuum chamber that limits the work size. The high capital cost of the equipment and necessary regular maintenance applicable for any equipment using vacuum system. High initial investment and high operating cost. Limited to thin parts in the range from 0.2 to 6 mm thick. Applications. Machining of titanium aircraft engine parts. Drilling fine holes, less than 50 mm. Cutting contours in sheets. Cutting narrow slots, 2-5 mm. Medical and electronics industries. Classification of non-traditional machining processes. This classification is carried out depending on nature of energy used for material removal. They are: mechanical, thermoelectric, chemical, electrochemical. Micro-ECM. Non-conventional machining system in which metal is removed by electrochemical process. Characterized as reverse electroplating means it removes metal instead of adding it. Normally used for mass production and for hard materials that are difficult to machine using conventional processes. Both external and internal geometries can be machined. Faraday's law of electrolysis. The weight of the substance produced during electrolysis process is directly proportional to 1. The current which passes. 2. The length of time of process. 3. The equivalent weight of the material. 2. Dissimilar metals are in contact with an electrolyte and anode loses metal to cathode. ECM vs ECMM. Improves resolution of anodic dissolution from millimeters to micrometers. Micromachining applies pulses in nanoseconds instead of direct currents. The schematic figure illustrates the principle of electrochemical machining. Anode is workpiece. Tool is the cathode. An electrically conductive fluid is used as electrolyte. The main functions of an electrolyte in ECM are: it carries the current between tool and workpiece. It removes the products of machining and other insoluble products from the cutting region. It dissipates heat produced in the operation. The essential characteristics of electrolyte includes: good electrical conductivity, Non-toxicity and chemical stability. Non-corrosive property. Low viscosity and high specific heat. High velocity flow over the electrode surface is one of the key factors of ECM. It is necessary to prevent crowding of hydrogen gas and debris of machining. Electrochemical machining, ECM kinematics, dynamics, working. Electrochemical machining, ECM kinematics, dynamics, working. Electrical power and control system of machining. Working parameters of the machine. Main subsystem. Power supply. Electrolyte. Tool. The control system. The machine. MRR depends on anodic reaction and current efficiency. Mass transport effects. Current distribution and shape evolution. Influence of various process characteristics. Nature of power supply and machining pulse. 1 DC supply. 2 pulse DC supply. Inter-electrode gap. Electrolyte type, concentration, and flow. 1 passivity electrolyte. 2 non-passivity electrolyte. Size, shape, and material of the tool. Applications. Nozzle plate for inkjet printer head. Production of high accuracy holes. 3D micromachining. Microelectrochemical milling. Wire electrochemical machining. Solid electrochemical machining. Oxide film laser lithography, OFLL. Micro and nanometer scaled surface structuring. Laser electrochemical micromachining, LECM. Advantages. ECM is well suited for the machining of complex two-dimensional shapes. Delicate parts may be made. Difficult to machine geometries. Poorly machinable materials may be processed. Little or no tool wear. Disadvantages. Initial tooling can be timely and costly. Environmentally harmful byproducts. Complicated tool design. Large power consumption. Micro-LBM. Laser beam machining is a thermal machining process which uses laser beam to produce heat and remove material from workpiece. Metal is removed from workpiece by melting and vaporizing of metal particles. Mostly used in cutting and drilling operations. Both metallic and non-metallic workpiece. Working principle. Electrons of an atom are provided an external energy source, to absorbs energy and get excited state. Electrons jump from their original energy level to higher energy level. It not stable condition of atoms, so this electron emits absorbed energy in the form of photons of light and come back to its original state. Spontaneous emission. Energy emitted by atom will have same frequency and wavelengths as that of stimulating source. The laser beam is focused onto the workpiece and can be moved relative to it. Optical energy is converted into heat energy upon impact and temperatures generated can be high to melt and slash or vaporize any material. Upon absorption of the laser energy, there is rapid rise in the temperature leading once again to melting and vaporization and material removal. Laser beam machining process and its parts. Mechanism of material removal. Absorb the laser energy. Rapid rise in temperature. Melting and evaporation. Material removal. Gas assist. Applications. Manufacture of microchannels and micro-holes in integrated chips and microchips. For drilling micro-holes. Surface micro-machining is characterized by the fabrication of micro-mechanical structures from thin deposited thin films. Used in machining threads in a single polyfiber and also used to give taper to the fiber. Advantages: easy capability of being automated, straightforward process monitoring, forceless and contactless machining, minor heat affected zone, marginal modifications to the microstructure, machining free of burr and bulging, high flexibility regarding design of tiny structures, high machining speed, high precision, constant machining quality, no additional tooling costs by wear, no solvent chemicals used, material removal rate controllable down to the nanometer scale. Disadvantages: the equipment required for micro machining is very costly than other cutting processes. Need highly skilled persons to operate micro machining systems. Material limitations, including crystalline and reflective materials. Reflected laser light can present a safety hazard. Thanks for watching this video. Please subscribe to this channel for more lecture videos. Until next time. Adios.